Hey everyone, today I'm going to do a full review of AP Physics C Mechanics, and this is going to be updated for the new exam. So you can use this to prepare for this year 2025's exam. Okay, our first unit is kinematics. So first let's start off with scalars and vectors. So scalars are something that have only a magnitude. Think of temperature, speed, and height. It's just a magnitude, it has no direction associated with it. But vectors have a magnitude and a direction. Think of velocity, displacement, and momentum. If you don't know what those are yet, don't worry, we'll go over it in the next few slides. But essentially, vectors have a magnitude and a direction. So maybe the magnitude is 5 and the direction is upward. And because of that, vectors can be expressed in unit vector notation. So generally, there's three directions, x, y, and z. We usually only use x and y because the z direction is like the third dimension. And we represent each of those with I hat, j hat, and k hat respectively. And to add two vectors together, essentially you need to add the components separately. And here I included an image of a vector. So you represent it with an arrow. So the longer it is, the more magnitude it has, and it's pointing in the direction of the vector. And you can also add two vectors with the tip to tail method, which on the bottom right I show here. This is so essentially if you put the two vectors, connect their tails together, then the emerging vector, you can find the direction as it will just go through the middle. Yeah. Okay. So now we're going to go over displacement, velocity, and acceleration. So we generally assume that the mass of a three-dimensional object exists at a single point, which is the center of mass. And the displacement is the change in position of an object, and it is a vector. So that's just x final, position final minus position initial. Also note that the average velocity is the displacement divided by the time interval it took to complete that displacement. So it doesn't matter, the distance traveled doesn't matter, it's just the final position minus the initial position. And one more thing, acceleration generally implies, it has to imply a change in velocity. Acceleration is defined as the rate of change of velocity. So velocity is changing. Velocity is a vector, so it has direction and speed. So one of those or both of those must be changing. An average acceleration is the change in velocity divided by the total time interval. So it's generally over longer periods of time. Okay, so here's some of the calculus part. So velocity, we define it as the displacement over time. So at an instant, it's dx dt. Acceleration is dv dt, the change in velocity over time. And note that you can connect position to acceleration by the second derivative. And because of the top, we can also do the bottom, what I wrote here. So position as a function of time is therefore the integral of velocity as a function of time. And velocity as a function of time is the integral of acceleration as a function of time. Okay, so how do we represent motion? So generally we separate the motion of an object into its x, y, and even z components separately. And these are the big four kinematics equations you should know. So final velocity equals initial velocity plus acceleration times time. And yeah, here are the rest of them too. The first three are on the equation sheet. The last one is not, but it's pretty self-explanatory. It just the change in position or displacement is the initial velocity plus the final velocity divided by 2 times time. And all of these equations assume a constant acceleration. If the acceleration is not constant, then you'll have to use calculus. Also, acceleration due to gravity is 9.8 meters per second squared, but the AP exam lets you use 10 meters per second squared. And the calculus definitions on the previous slide imply the following. It implies that the instantaneous velocity is the slope of the tangent line of a position time graph, because v is equal to dx dt. Instantaneous acceleration is the slope of the tangent line of a velocity time graph, so acceleration equals dv dt. And displacement is the area under the curve of a velocity time graph because of the integral definition. And the change in velocity is the area under the curve of an acceleration time graph again because of the integral definition. Okay, now we're going to go over reference frames and relative motion. So a reference frame determines the motion seen by an observer in that frame, and measurements from one frame can be converted to another. So the observed velocity that someone sees an object moving at depends on the object's actual velocity with respect to the ground and the observer's velocity with respect to the ground. Because what if the observer is moving? So generally for these types of problems, try to visualize a scene and just use common sense and logic to solve it. So here in the bottom, I included a diagram of, let's say, me on the ground. I'm moving 5 meters per second to the left, and the bus is to the right of me as moving 10 meters per second to the right. So the bus with respect to the ground is 10 meters per second. Me with respect to the ground is 5 meters per second. And since I'm moving the opposite way as the bus seems to be going faster from my reference frame. So the bus is actually moving 15 meters per second to the right in my reference frame because I'm moving 5 meters per second to the left and our distance is increasing. Okay. And motion can also be in different dimensions, not only one. So motion in 2 or 3 dimensions is separated into its x, y, and z components. And essentially the important thing you need to know is that an object's motion in the x direction will not affect its motion in the y direction. Because velocity and acceleration can be vastly different in each dimension, and they'll have no relationship with each other if they're in different dimensions. So projectile motion is an example. So essentially, an object will have a constant acceleration due to the gravity downward, and that causes the y velocity to change. But the x velocity is constant because there's no acceleration in the x direction. But the x direction does not change, which is why you get the parabolic path. Although my drawing was pretty bad, not that symmetric, that's what it'll look like. But imagine it's symmetric on both sides. Okay, now on to Unit 2, Force and Translational Dynamics. Okay, so first we're going to go over systems and center of mass. Generally, we can treat interactions of objects within an area as a system, and we can treat a system of objects as a single object, and that object will be located at its center of mass. Note that objects within a system can behave and likely will behave differently from the whole system as a whole. And the location of a system's center of mass with different whole objects in the system can be calculated. We can also do it for non-uniform solids. So usually for uniform solids, the center of mass will be at the geographic center. But for non-uniform solids, we consider them as a collection of masses, integral masses dm. And we sometimes use the linear mass density, which is the amount of mass per unit length, or lambda, to solve it. And then we model a system as a singular object located at the system center of mass. So for whole objects in a system, the center of mass is the sum of the objects times their mass, sum of the object's position times their mass for each object, add them all up, and divide it by the total amount of mass. And the center of mass of the system can be found using this integral I wrote here, the integral of r dm over dm, integral dm. And note that lambda is equal to dm over dr. That's the linear mass density. And because of this, you can replace lambda for the dm. So you get lambda dr equals dm, and you replace that dm in the upper integral. And note that the integral of dm is just the total mass. So the bottom becomes just m, and then you can solve that integral. Also note that the total mass of the system can also be the integral of the density as a function of r times by dv. Okay, so forces are vectors. So that means they have magnitude and direction that describe interactions between systems. And a system and an object it can never exert a net force on itself. It's just impossible because, yeah, it just won't work. If you push yourself one way, then because, well, we'll go over it later, but essentially it's because of Newton's third law. And contact forces involve touching and are macroscopic effects of interatomic electric forces. And we often use free body diagrams to represent a system. So here we have this person standing. The only two forces exerted are the normal force upward and the force of gravity downward. And because he's not accelerating, they're equal. Below, I have an object on a ramp accelerating downward on a rough ramp. And we have the force of gravity downward, the normal force perpendicular, and the force of friction up on the ramp because the velocity is going downward. Okay, Newton's third law. So Newton's third law states that every force has an equal and opposite force exerted on it. And that's why you cannot exert a net force on yourself because an equal and opposite force will cancel it out. And note that when you exert a force on another object, you might be wondering why the forces don't cancel. It's because they're on different objects. When I push my water bottle, the water bottle pushes me. So they can't cancel because we're two different objects. Another force you need to know is tension force, which is the result of forces from really small segments of strings, chains, cables, and similar systems. Note that we assume ideal strings have no mass and no stretch under tension. And ideal strings, if these are satisfied, then they will have constant tension throughout the entire string. Note that the above may not apply for non-ideal strings. Non-ideal strings may have mass and may have stretch. And an ideal pulley has negligible mass, an ideal string, and it rotates about an axis with negligible friction. Okay, now on to Newton's first law. The net force on a system is the vector sum of each force on the system. I made a typo. It's not the vector system, it's the vector sum of each force on a system. And if the net force on a system is zero, then the object must be in equilibrium. That means there's no acceleration. Essentially, Newton's first law implies that a system has a constant velocity and no acceleration if the net force exerted on the system is zero. And forces can be separated into different dimensions, and a force in the y direction will not affect an object's motion in the x direction. As we mentioned previously in the projectile motion slide. Okay, Newton's second law states that F net is equal to the mass of an object times the acceleration. And Newton's law of universal gravitation states that the force of gravity exerted between two objects are equal, and it's equal to g, a constant, times m1, mass of one object, times the mass of the second object, divided by the distance squared. And the distance refers to the distance of the object's center of masses. Also, the force of gravity is always attractive, and it is exerted on the system's center of mass. The force of gravity, the weight, can also equal the mass times the acceleration due to gravity. And we can essentially set these two to be equal and solve for what the gravitational field, acceleration due to gravity, really is. I did that on the bottom. So essentially m1 cancels out and you get g, lowercase g is equal to big G m2 over r squared. Okay, continuing on gravity, the unit is meters per second squared or newtons per kg. And one more thing is that the apparent weight is the weight you feel, normal force. So when you're in free fall, you feel weightless. That means there's zero apparent weight. There's nothing pushing on you, assuming no air resistance. An apparent weight does not always have to equal your normal weight. The force of gravity doesn't always have to equal that. Here on the bottom right, I included a diagram of when it's not equal. Let's say a box is on an elevator, it's accelerating downward at 3 meters per second squared. So we can solve Newton's second law for it. So minus ma is equal to Fn minus mg because acceleration and the force of gravity are in the same direction. And we solve for Fn, which is equal to mg minus ma. Because of that, it can't be equal, like Fn is clearly smaller than mg because it's minus ma2. And inertial mass is the measure of mass of how well an object resists change. And gravitational mass relates to the force of gravity. So both of these were experimentally verified to be equal. All right, Newton's shell theorem. So Newton's shell theorem is for the net gravitational force exerted on an object by a uniform spherical shell. So note that inside the thin shell, the net gravitational force in an object inside will be zero because all of the individual mass dmg, so dm times g, all of them will cancel out. And outside the shell, we treat the shell's mass as being concentrated at the center. And then we just use the normal gravitational force equation. Okay, so inside a normal sphere, so not a shell, a sphere of uniform density, the net gravitational force is purely due to the mass of the sphere, a distance less than or equal to the object's distance from the sphere's center. And because of this, the gravitational force exerted on an object inside a uniform sphere is derived to be proportional to the object's distance from the sphere's center. So I sort of did that on the bottom right. For a uniform sphere, I drew an object located here, and I drew I drew it in 2 dimensions, but it's 3 dimensions. I drew the appropriate circle of all distances r less than or equal to the object's distance from the center. And yeah, so what you can do is use the gravitational force equation g m1 m2 over r squared, and the mass can be equal to rho, the uniform density, times 4/3 pi r cubed. And the density, because it's uniform, is just the total mass over the total volume. And that's how the mass m2 of the sphere, which is less than a distance r from the object, is equal to the density times 4/3 pi r cubed. And usually you'll be given the density. Yeah. Okay, friction force. So there are 2 types of friction. Kinetic friction occurs when 2 surfaces are in contact and they move relative to each other. And the force opposes the motion of each surface relative to the other one. Also, the coefficient of kinetic friction times the normal force is equal to the force of kinetic friction. The coefficient of kinetic friction just depends on the surface in contact. And the normal force is the perpendicular and upward force from a surface. So static friction is another type of force that occurs when 2 objects are not moving relative to each other. And static friction is an adaptive force and is less than or equal to the coefficient of static friction times the normal force. The max static friction force is the coefficient of static friction times the normal force. And because static friction is adaptive, it'll always be equal to the pressure being put on it. And often, well, actually in basically every case, the coefficient of static friction is greater than that of the coefficient of kinetic friction between 2 of the same objects. And here's an example. So let's say I have this ramp, I have an object on it, and I'm slowly raising the angle theta. So as I raise the angle theta, then the object is going to be more likely, like there's more of a component of gravity pushing the object down the ramp. And I drew the free body diagram for it up there. So essentially, there's a friction force, static friction force acting up the ramp, normal force perpendicular, and force of gravity straight downward. We can split the force of gravity into components. So the component down the ramp is mg sine theta. So that means mg sine theta, that's the force of gravity down the ramp. That's opposing the force, or the static friction force opposes that. And that static friction force is equal to Fn times the coefficient of static friction. And Fn here, because the object is not accelerating it's not accelerating through the ramp, it's just equal to mg cosine theta, to the other component of force of gravity. So essentially, yeah, that's the equation. Mg sine theta minus mg cosine theta times the coefficient of static friction. And eventually at some theta, the mg sine theta is going to be bigger than the mg cos theta times the coefficient of static friction. Because sine theta increases from 0 to 90, cosine theta decreases from 0 to 90. And below, I drew a graph of what it's going to look like, of what the force of friction look like. So the force of static friction is adaptive. So it's slowly going to increase as the angle theta increases. But eventually, once the object starts sliding, it's just going to be a constant kinetic friction force. Now into spring force. So an ideal spring has negligible mass and exerts a force that is proportional to the change in length from its relaxed length. And that's governed by Hooke's law. So the force is equal to minus k times the change in x. And this force is always directed toward the equilibrium position. Note that a collection of springs, we can treat it as a single spring with an equivalent spring constant. So I included the two types of collections you need to know, springs in parallel and springs in series. So for springs in parallel, this is the equation used to find the equivalent spring constant. So 1 over k equivalent is equal to the sum of 1 over the individual spring constant of each spring for series. So that's for the right one. And for parallel, the one on the left, you essentially just add the spring constants because in parallel, these springs are supporting each other, like they're working together. But in series, if one spring gets compressed, the other gets stretched, so it's a bit weirder. So yeah, just use these equations. Now on to resistive forces. This might be the most calculus-heavy part of the unit. So resistive forces are like air resistance, and they're velocity-dependent forces. They act in the opposite direction to an object's velocity. Sometimes it's often air resistance, sometimes you might have to do it with friction too. And we use separation of variables and integration to solve it. So the terminal velocity is the maximum speed achieved by an object when the net force exerted on the object is zero. And the force of air resistance is the perfect example. So initially, when an object is free falling and there is air resistance, the force of gravity is going to be much greater than the force of air resistance. But as time goes on, eventually the force of air resistance will likely, in perfect scenarios, the force of air resistance will catch up and equal the force of gravity. Because, yeah, and at that point, then the object's moving at a constant velocity because the net force is zero. So here's how you do it. You do m, so Newton's second law, ma is equal to the net forces exerted on an object. You do m dv dt because dv dt is also equal to acceleration. That's equal to mg minus kv, which is kv is the force of air resistance. But then you separate v onto one side, all the v's onto one side, and all the non-v's onto the other side, and the dt on the other side, and then you just integrate and solve. And finally, circular motion. So circular motion is essentially a state when an object is changing direction constantly. And that changing direction is due to a centripetal force. And centripetal force causes centripetal acceleration, and that's essentially just the component of an object's acceleration directed toward the center of the object's circular path. And that's equal to v squared over r. So the speed squared over r. Note that it's a scalar, it's speed, not velocity, because it's squared. So direction gets canceled out. And centripetal force is thus the net force directed inward. So it's not an individual force, it's just the net forces exerted inward. And it causes an object to change direction and move in a circle. So when an object is moving at a circular loop, at the top of the circular loop, the minimum speed to maintain circular motion is v is equal to square root g over g times r. And you can solve it using centripetal acceleration, centripetal net force. And different forces in different scenarios, like static friction and normal force, can contribute to net centripetal force. So what you generally do is just find the forces, draw a free body diagram, find the forces acting inward, and equate that to mv squared over r. So I did that here. So let's say I'm spinning an object on a string in a circle. At the top of the loop, there's the force of tension downward and the force of gravity downward. And those two added equals the centripetal force at the top of the loop. So minus t minus mg equals mv squared over r. And continuing on circular motion, an object can also be accelerating tangentially. So not just its direction changing, but its speed changes too. So the net acceleration of an object is equal to the vector sum of the centripetal and tangential acceleration. And the time to complete a full circular path is the period and is represented as a big T. The frequency is 1 over period and is the number of revolutions per second. And the period for an object moving at a constant velocity through a circular path is 2 pi r over v. And for a satellite in a circular orbit, t squared, the period squared, is equal to 4 pi squared r cubed over big G times the mass of the planet, big M. Okay, on to unit 3, work, energy, and power. Let's start with translational kinetic energy. The translational kinetic energy is equal to 1/2 times the mass times the velocity squared. And note it's a scalar quantity because velocity is squared. And different observers may see different velocities, and thus in different reference frames, objects will be seen as having different kinetic energy. And yeah, translational kinetic energy is generally called the energy of motion. Let's go on to work now. So work is the amount of energy transferred into or out of a system by a force exerted over a distance. And a conservative force is a force that is path independent. So it only depends on the initial and final system configurations. Think of the force of gravity. So we're going to go over it later, but essentially it only depends on the height. So that means the net change in potential energy of a system will be zero if the system returns to its original configuration for a conservative force. And conservative forces generally have potential energies associated with them. That's why the force of gravity is a conservative force. It has gravitational potential energy associated with it. And the spring force is conservative because it has spring potential energy associated with it. But the force done by a non-conservative force is path dependent. So like the force of kinetic friction and air resistance. As you travel more, the force of kinetic friction does more work and slows down an object more. Same with air resistance. And work is a scalar quantity, but we can assume or we have implied that it's positive, as physicists positive or negative. Positive means energy is added to the system. Negative means energy is taken away from the system, or it could just be zero. So the energy of the system is unchanged. And below is the definition of work. So work is equal to the integral of the force of a force acting over a distance r times dr, dotted with dr. And when you solve this integral, you'll get the work done. But if the force and the distance are constant, but the angle, there's an angle, it's just equal to fd cosine theta, where theta is the angle between the force and the distance vectors. All right, continuing on work, only the parallel component of force to the displacement of the object causes the work. The perpendicular component only changes the direction, as we showed, because the perpendicular component is essentially a centripetal force. That's why the cosine theta eliminates the perpendicular component. And the work energy theorem states that the change in an object's kinetic energy equals the net work done from all forces on an object. And energy can also be dissipated by friction. So that's equal to the force of kinetic friction times the distance times cosine theta. That's the net work done, and it's negative, and it's the energy dissipated. And again, because of the work definition on the previous slide, work is also equal to the area under the curve of a graph of the force, the parallel force to displacement versus the displacement. So F cosine theta as a function of displacement. Okay, now into potential energy. So a system of two or more objects will have a potential energy if the objects interact with each other via conservative forces. So potential energy is a type of energy related to the position of an object within a system. And we often choose the zero potential energy point because choosing it can be useful in solving a problem. And as I mentioned earlier, only conservative forces have potential energies associated with them. That's the force of gravity, conservative, force of the spring force, but that's not the force of air resistance. That's not normal force. That's not force of friction. And we can connect the change in potential energy of a system with the conservative force with the following integral. The change in potential energy is equal to the negative integral from A to B, from two states, two positions, of FR dot dr. So it basically is just the opposite of the work done. And we can also associate the force to be equal to minus du as a function of x, dx. And there are a few types of equilibrium you need to know. So stable equilibrium is where the displacement in the object's position will result in a force accelerating the object back to its equilibrium position. But unstable equilibrium is where the displacement in an object's position will result in a force accelerating the object away from the equilibrium position. So below, I included a few examples. So stable equilibrium on the left, when an object moves to the right, it's going to be pushed down by like the ramp, and you can just visualize it. In the middle, when the object moves to the right, it's just going to keep going down. And on the end, when it moves to the right, it's just going to stay there. And that's neutral equilibrium. So when you graph potential energy as a function of position, stable equilibrium positions are where the potential energy will be a local minimum. Unstable equilibrium positions will be where the potential energy has a local maximum as a function of position. All right, continuing on potential energy. The elastic potential energy of a spring is given by 1/2 k times the change in x squared, where the change in x is the distance the spring has been stretched or compressed from its equilibrium position. And the total potential energy of a system is the sum of the potential energy of each pair of objects in that system. Note that the gravitational field, the acceleration due to gravity, on the surface of a planet, if we assume it to be around constant and equal to g, minus 9.8 meters per second squared. But for planets and stars, for planets and stars, we don't use that g. Instead, we use this equation. So you can get this by doing the integral of the force of gravity, which we showed earlier. But essentially it's equal to minus big G m1 m2 over r for planets and stars in space. But for objects near the surface of a planet, it's equal to mgh, where h is the height above the ground. And energy can also be conserved. A system with only one object has only kinetic energy. It cannot have potential energy. But a system with objects interacting via conservative forces can have both kinetic and potential energies. The total mechanical energy is the sum of a system's kinetic and potential energy. And a closed system with no outside interaction will have a constant total energy, and energy may be transferred in different forms. The work being done on the system means that energy is transferred between the system and the environment. So the total mechanical energy, again, is equal to the kinetic energy plus the potential energy of the system. Now we're going to power. So power is the rate at which energy changes with respect to time. So the average power is the change in energy over the change in time. It's also equal, since work is the change in energy, it's also equal to the work done in a system over the change in time. And the instantaneous power is just, we do it with derivatives. So dw dt. So the derivative of work with respect to time is instantaneous power. And we can also associate this to be equal to FV cosine theta. Because, so let's say the work done as a function of time, work is just F times d. And distance over time, assuming is velocity, assuming it's a constant velocity and a constant force. So it's also just FD cosine theta of v. Because work is FD cosine theta. Our next unit is linear momentum. So linear momentum is a quantity defined by the following. The symbol is p, and it's equal to mass times velocity. And because it's mass times velocity, mass is a scalar, velocity is a vector, so momentum must be a vector too. And its direction is the same as the direction of velocity. We often use momentum to analyze collisions, and the initial and final states of a collision are primarily focused on. A special type of collision, known as an explosion, is where the forces internal to a system move the objects apart. And momentum, P is equal to m times v, as I mentioned, and both P and V are vectors, which is why they have the vector symbol. Okay, now what is the change in momentum? We define that to be impulse. So impulse is a vector quantity, and it has the same direction as the net force exerted on the system. And impulse is also equal to the area under the curve of the net external force versus time graph on a system. And the net external force in the system is the slope of the system's momentum versus time. So we get the following like this. So the impulse is equal to the change in momentum and is equal to the integral of F net as a function of time dt from t1 to from two time intervals, t1, t2. That's equal to the change in momentum and the impulse on the system. Additionally, we can rearrange it to get that the F net on a system is equal to the derivative of the momentum with respect to time. And because of this, all of our because of this, that's how we get the connections to the graphs. So that is impulse being the area under the curve and net external force being the slope. The impulse momentum theorem states that the total change in a system's momentum has to be equal to the impulse. And we kind of hinted on this in the previous slide, but so the first image I included, we wrote that in the previous slide, but the bottom one, we hinted at it. So F net is equal to dp dt. We get this by rearranging the integral, that change in p equals the integral of F net dt. So F net is equal to dp dt, and essentially since p is equal to m times v, we use product rule, and we get m times dv dt plus v times dm dt is equal to F net. This is where Newton's law comes in, Newton's second law. This is the definition of Newton's second law. In Newton's second law, we assume the dm dt is zero. So the second part of the expression goes to zero. So F net is equal to m dv dt equals ma. But in reality, this is what the full-fledged form is. So you might have questions where the mass is constant and the velocity is changing, or even when the velocity is constant and the mass is changing. And now we're going to go over conservation of linear momentum. So a collection of objects, we can think of it as one system with one center of mass velocity. And a system center of mass velocity can be calculated, and it'll be constant if there's zero net external force on the system. A system's total momenta equals the sum of the individual momenta of each object in the system. And momenta is a vector, so you have to keep that in account. Inside a system, an individual object's momentum will only change with an impulse. But the other object in the system, which caused the impulse, must experience the same but opposite impulse because of Newton's third law. And it's just force times time. That's impulse, basically. And the force are constant, the time are constant. So that means the net impulse on the system cancels out, leaving the momentum conserved. So in a system, the objects can interact with themselves, but the total momentum of the entire system will be constant. Only the net external force on the system matters. And yeah, so the velocity of the center of mass of the system is equal to the sum of the momentums of each individual object divided by the sum of the total mass of the system. Okay, and there are two main types of collisions you need to know, elastic and inelastic. Elastic collisions are where the system's initial kinetic energy equals the system's final kinetic energy, so the kinetic energy doesn't drop. And this is for the entire system, not each individual element. But in an inelastic collision, the system's total kinetic energy decreases, It'll decrease because a non-conservative force transforms that kinetic energy into other forms. In a perfectly inelastic collision, objects will stick together. And because they stick together, the kinetic energy has to decrease. Why, you may ask? Because momentum is conserved. And if momentum is conserved, the velocity will have to, so then m times v1 equals the m total times v2. And the mass increases, so the velocity must decrease by a proportional amount. But kinetic energy has a square dependence on velocity. That's why. And here I included an example so you can see how it works. So an object mass m is moving at v to the right. It collided with an object of 3m, and they move together at a final vf. Because of conservation of momentum, we can solve for the vf. And if you want, you can solve for the initial kinetic energy, 1 over 2 mv squared, and the final kinetic energy, 2m times v squared over 16. And clearly, the final kinetic energy is smaller. On to Unit 5, torque and rotational dynamics. So let's start with rotational kinematics. So angular displacement is how much a rigid system rotates across an axis. So it's the change in theta equals theta final minus theta initial. And for rigid systems, their shapes do not collapse during rotation. Think of something solid like a rod rather than a flimsy paper. Generally, either clockwise or counterclockwise direction can be considered positive, and the other will be negative. In the problem on the AP exam, they'll usually state it for you. And again, we can treat different objects in a rotating system as one object, one center of mass, and one rotation. And generally, rotational kinematics is analogous to linear kinematics. So that's why the following equations apply. And these are all constant alpha equations. So omega is analogous to velocity, which is omega is angular velocity. Angular acceleration, or alpha, is analogous to acceleration. And theta position is, or theta angular position is analogous to regular position. And all of these equations are just the big four kinematics equations, but in rotation form. Okay. So all points in a rigid system move at the same angular displacement, angular velocity, and angular acceleration. And we can connect the angular parts of kinematics to the translational parts by multiplying by r. So if we have this object rotating at an angular velocity of omega, at a distance r away, the velocity is r times omega. The arc length, change in position, is r times change in theta, and the translational acceleration is r times alpha. Now going to torque. So torque is the result of the force component perpendicular to the position vector from the axis of rotation. The lever arm is the perpendicular distance from the rotation axis to the exerted force. And we will use force diagrams to analyze torque rather than a free body diagram. And we often use the right-hand rule to determine the direction of torque. So just curl your hand in the direction of the force and the r, and then the resulting, so you have three fingers, right? Put the thumb in the direction of r, the r vector, your pointer finger in the direction of force, and your middle finger will point in the direction of torque. But honestly, you can just reason it out. Just like think if is it gonna rotate clockwise or counterclockwise? Yeah. Here's an example. So let's say that we have this beam at the center. We have this mass m a distance 5 away, this mass 2m a distance 9 away. I calculated the net torque in the system. 18 mg minus 5 mg is equal to 13 mg, and it's going to be counterclockwise. You can literally just reason it out because 2mg is a further distance away. Also, here's an example of the lever arm theorem. So I have this force acting on this rod. We can continue the force upwards, and this distance I drew, which I drew an arrow to, that's the lever arm. And that lever arm is at a 90-degree angle from the force vector if you continue drawing the force upward. So the force times the lever arm is equal to torque, or we can take the perpendicular direction of the force here and then just look at the distance. And yeah. Okay, rotational inertia is the rotational analog to regular mass. So it's just a rigid system resistant to change in rotation. For an object rotating at a distance r from an axis, the rotational inertia is the mass times the radius squared. So the total rotational inertia of a system is the sum, I wrote if, but it's really is the sum of the rotational inertias of each individual object. And we can consider a solid as a collection of masses dm. The smaller the distance from the rotational axis, the smaller the contributed rotational inertia is. So in integral form, I, rotational inertia, equals integral of r squared dm for a mass dm and a distance r squared away. And the parallel axis theorem states the following, that the new rotational inertia, we can sort of, the rotational inertia of an object around a different axis, which is not the center of mass, is equal to the rotational inertia about the center of mass added to the mass multiplied by the distance from the center of mass to that parallel axis squared. So the new rotational inertia equals the rotational inertia about the center of mass plus the total mass of the system times d squared. Okay, and an object's state of translational equilibrium will never affect its rotation and vice versa. Just like how different movement in different dimensions don't affect each other. And rotational equilibrium means that the net torque on a system will be zero. So when a system is in rotational equilibrium, it will have a constant angular velocity. So if the net torque is not zero on a system, then the system is not in rotational equilibrium, and the system must experience an angular acceleration. It's very similar to force and net force in translation. And this is Newton's second law in rotational form. Essentially just torque net equals alpha, angular acceleration, times the moment of inertia of the system. And we can rearrange it to be the following. And yeah, again, we do linear and rotational analysis separately. Okay, energy and momentum of rotating systems. So rotational kinetic energy of a rigid system is 1/2 I omega squared. The total kinetic energy is the sum of its kinetic and rotational kinetic energies. So that's equal to 1/2 I omega squared plus 1/2 mv squared. And rotational kinetic energy is once again a scalar. An object can have either or both or none of linear and rotational kinetic energy. So how did we get that rotational kinetic energy is 1/2 I omega squared? Well, let's assume there's a mass a distance r away from the axis of rotation, and it's rotating at an angular velocity of omega. So we can say that v is equal to r omega, right? Because we proved that earlier. So the kinetic energy of the object is equal to 1/2 mv squared, but v is equal to r omega. So 1/2 m r omega squared. And mr squared is just equal to I, because there's an object at distance m away from the center. And that's how we get it's equal to 1/2 I omega squared. Torque can transfer energy into and out of a rigid system, but the torque has to be exerted over an angular displacement, just like work has to be exerted over a displacement. And the area under the curve of a graph of torque versus angular position in radians gives the work. So we get work is equal to the integral from theta 1 to theta 2 of torque with respect to d theta. And the magnitude of angular momentum of a rigid system about an axis is equal to I omega. No, it's similar to the momentum, linear momentum of a system, m times v, but just in rotation counterparts. So most of rotation, just if you're confused, just try thinking about the linear counterpart. And the angular momentum of a single object, so let's say an object's just moving in translation, that object can be said to have angular momentum about a point. And that's equal to r cross momentum. So r cross m times v. So below, I included an image to show what I'm saying. Let's say I drew a dot here at the bottom left. Let's say that's the position where that's the axis we're looking at. And let's say there's a massive object M moving at a velocity v in the east direction, perfectly east. And let's say that there's an angle theta between the velocity and the r vector. So the L angular momentum from that object is equal to mvr sine theta. Because that's how we get, that's r cross p. R cross p will give the sine theta. And that sine theta is equal to r prime. So it's just the vertical distance, in this case, just the vertical distance. So no matter how far the object moves to the right, to the east, the r prime, the vertical height will be the same. And angular impulse is equal to the integral of torque dt. And angular impulse will have the same direction of torque. Because of this, the net torque is also the slope of the graph of the angular momentum versus time. And angular impulse is also the area under the curve of a torque versus time graph. And the change in angular momentum is equal to the angular impulse and equals the final angular momentum minus initial angular momentum. So below, torque net is equal to dl dt. So again, this is similar to Newton's second law, the real version of Newton's second law. This I d omega dt, which is angular acceleration, plus omega di dt. But generally, you won't have problems where well, you might actually. You might have problems where the moment of inertia is changing, but it'll be pretty simple. And just as linear momentum is conserved, angular momentum is also conserved. The total angular momentum is the sum of the angular momentum of the system's parts around an axis. The angular impulse exerted by one object on another is equal and opposite to the angular impulse exerted by the other object on that one. And that's Newton's third law. Angular speed can change without angular momentum changing. So if the moment of inertia decreases and there's no external force on a system, external torque on a system, then the angular speed of that system must increase because angular momentum must be conserved. A net torque on a system indicates that the system's angular momentum is changing, but zero net torque indicates a constant angular momentum. So I do a diagram here. Let's say we have this figure skater with their arms wide out, rotating at an angular velocity of omega. Then if they bring their arms in, the angular momentum must be constant, but omega increases because the moment of inertia decreased. Now we're going on to rolling. So rolling without slipping is when an object just rolls on the ground and it's not sliding at all. It's just rolling. That means no energy is dissipated from static friction because it's rolling and there's no kinetic friction. So when an object is rolling, static friction is exerted on the object. But if an object is slipping, then kinetic friction is acting and it will dissipate energy. And the equations to the right do not apply if it's not rolling without slipping. Note that the total kinetic energy of a system is the sum of its translational and rotational kinetic energy, as we mentioned earlier. So the following equations on the right apply if an object is rolling without slipping. And we've seen these equations before if an object is like rotating about an axis, but these will apply if an object is rolling without slipping. So when an object is rolling down a ramp without slipping, there's force of gravity down, normal force perpendicular, and a force of static friction up on the ramp. And that force of static friction is what causes the rolling. Now on to motion of orbiting satellites. In a system with a large central object and an orbiting satellite with mass negligible compared to the central object, we can ignore the central object's motion. So in circular orbits, the system's total mechanical energy will be constant because the gravitational potential energy minus g m over r, that's constant because the r is constant. And if that's constant, then the kinetic energy must be constant because the total mechanical energy of the system is unchanged in the absence of external forces. And the angular momentum will also be constant. But in elliptical orbits, the system's total mechanical energy will be constant still, the sum of kinetic and potential energy, and the angular momentum will be constant, but the kinetic and gravitational potential energies can both change because the radius is variable. So the gravitational potential energy will change, but the kinetic energy must also change to counteract that. So the sum will still be constant. And continuing on orbiting satellites, we define the escape velocity of an object equal to the velocity needed to escape a planet's gravitational pull. And when this happens, the mechanical energy of the object planet system will be equal to 0. And if an object reaches escape velocity at the surface of the planet, it will have 0 speed and infinite distance away. So at the bottom, I showed how you solve for it. You do 1/2 m times the v, and this v is the escape velocity squared, equals big G times big M times little m over r. And this is just saying that the kinetic energy of that object is equal to the gravitational potential, the magnitude of gravitational potential energy at that point. Because gravitational potential energy is really minus G at G big M small m over r. So 1/2 mv squared minus gravitational potential energy equals 0. So when you move that minus to the other side, it becomes positive. And you can solve for the escape velocity like this. And on the right, I included what happens when an object is in circular orbit. So gravitational potential energy equals minus G m1 m2 over r. And because it's in circular motion, that means m1 v squared over r is equal to G m1 m2 over r squared. Because G m1 m2 over r squared is the gravitational force, and that's the only force contributing to the centripetal motion. So we cancel out the r's on the bottom, and we divide by 2. So the kinetic energy, 1/2 m1 v squared, is equal to G m1 m2 over 2r, which is just 1/2 the magnitude of gravitational potential energy. So then we add this to the gravitational potential energy, minus G m1 m2 over r, and we get the total mechanical energy, and the total energy of the system as a whole equals 1/2 UG, where UG is the gravitational potential energy of the system. All right, final unit, oscillations. Okay, so first let's define simple harmonic motion. So periodic motion is defined as a repeating motion, like a rocking chair. Simple harmonic motion is a type of periodic motion. It exists when there's a restoring force and an equilibrium position in a system's motion, where the restoring force is proportional to the object's displacement from equilibrium, and the force is directed to the equilibrium position. At the equilibrium position, the net force exerted on the system must be 0. So we can write this in equation form as MAX in the, let's say, the x direction equals the restoring force, and that's equal to minus k change in x, where k is some constant we don't know, and it's minus because it points back to the equilibrium position and opposite to the displacement, and it's proportional to change in x. Okay, and we define period as 1 over frequency and also equal to 2 pi over omega, where omega is the angular velocity or angular frequency. Yeah, don't get confused with angular frequency and angular velocity. So in simple harmonic motion, we have omega equal to angular frequency, and it's defined as it is up there with respect to t and f. And below, I have two equations which define the period for a spring mass oscillating system and the period for a pendulum mass oscillating system. These equations will be on the equation sheet. You just need to know when to use them. So you'll use them if they ask for period or frequency, and be sure to use the right one. So use the first one for spring mass, the second one for pendulum mass. Okay, so how do we analyze simple harmonic motion? So the displacement, velocity, and acceleration vectors can all be modeled. The sine and cosine can be interchanged in the equation that I wrote below. So x is equal to a cosine 2 pi ft. And we mentioned on the previous slide, 2 pi f equals omega. And we can take the derivative of x with respect to time to get the velocity in simple harmonic motion. That's minus a omega sine omega t, where omega is equal to 2 pi f. And again, we take the derivative to get the acceleration of the function of time. Now, for each of these equations, we have the max. So x max is a, v max is a omega, and a max is a omega squared. We have the max times the cos times the sinusoid. And below we have what it looked like. That's what a sinusoid looks like. And yeah. Also, note that acceleration has to be equal to minus omega squared x. This condition must be true for simple harmonic motion to occur. And again, x is equal to a cosine omega t, potentially plus some other angle or plus something else, plus some other constant. It doesn't have to always start at a max. And velocity is equal to the derivative of x. Acceleration equals the derivative of velocity. Okay, on to resonance. An external force on a system can cause resonance to occur. And resonance will only occur if the force is exerted at the frequency of the oscillating system and it increases the amplitude. So the force has to be exerted at the right time, not like when an object is at a certain position to increase its amplitude. And it has to be exerted like as the system moves in the correct position. Because note that there's another force, the restoring force also being exerted. Also, changing the amplitude will not change its period. We wrote the period equation on a previous slide, but there's no amplitude in that. If the amplitude increases, the force will just increase too. And if it decreases, the opposite will be true too. The period stays the same. Okay, what does energy look like in simple harmonic motion? So the total energy of a system in simple harmonic motion is the sum of its kinetic and potential energy. And usually the total mechanical energy will remain constant, assuming no non-conservative forces like kinetic friction or air resistance. The kinetic energy is the max when the potential energy is the minimum, and the potential energy is the max when the kinetic energy is the minimum. So at the center of a spring oscillating system, the kinetic energy will be a max. At one end, the potential energy will be a max. And that energy, the total energy, mechanical energy, is equal to 1/2 k amplitude squared. Because at one end, that's what its potential energy is, while its kinetic energy is 0. Okay, on to simple and physical pendulums. So we defined simple pendulums previously. We found the period equation for it. But a physical pendulum is when a rigid body oscillates. And a simple pendulum can just be thought of as a physical pendulum where the hanging object is modeled by a point mass a distance away from the pivot point. A torsion pendulum, on the other hand, is where the restoring torque of that pendulum is proportional to the angular displacement of the rotating system. And for a torsion pendulum, the moment of inertia, I, times the angular acceleration equals minus k times the change in theta. And the moment of inertia in the following period equation that I included is that about the axis of rotation. So for a physical pendulum, period equals 2 pi square root of I over mg d center of mass. So I is the moment of inertia about the axis of rotation. The d center of mass is the distance from the axis of rotation to the center of mass. And yeah, so the torque will be equal to minus mgd sine theta. And we can assume sine theta to be theta. The torque is equal to minus mgd theta equals I alpha. And again, the simple harmonic motion equation, d theta squared over dt squared, d squared theta over dt squared, sorry, equals minus omega squared theta. And yeah, that's an entire review of AP Physics C. Thank you for watching the video. If you have any questions, please comment them. We'll try to answer as many, hopefully all, that we can. Best of luck on the exam.